I don't think many of you need an introduction to Chiranjeev Bhattacharya, faculty at Indian Institute of Science, and a very well-known name in the machine learning space in India and abroad. So without much further ado, Chiru.
So thank you, Satish. So as we said, now all talks in this session should begin with campaigning for PJN. So let me do my bit, and also end with that. So we'll do that. So having got that out of the way, now I would like to thank the organizers for inviting me. So the organizers asked me, PJN or Satish asked me that can you give an overview of things which you'd like to do, like unsupervised learning? Then I didn't ask them, but they said 20 minutes. I said, it's not possible. So state of the art in unsupervised learning, you can talk for hours. Of course, all scientists like to talk for hours. That is the thing. So we changed the topic slightly. It's the state of unsupervised learning. So here I would like to confine myself to broad comments. You don't have to agree to this. If you disagree, please put up your hand. We'll have a more meaningful conversation. So I like to drive this talk like that. So yeah, so I am Chiru, and today we're going to discuss state of unsupervised learning. Now, see, there has been a lot of talk about AI being a big disruptor, right? Recently, we had a very exciting debate over the internet when we heard some of the seminal personalities like Elon Musk and Mark Zuckerberg had a spat about AI is good or bad. But Elon Musk made this comment that AI represents a fundamental risk to the existence of civilization. Now, even in the morning session, we heard that governments are worried, right? So, and I think this question requires some thought. I don't think Elon is looking for publicity. He's already very well known. And also, Mark Zuckerberg is also knows, though Elon says he doesn't know AI, but I think this guy also is very smart. So, having said that, then let's wonder for a moment and ask, what is AI? So now AI, as in the previous morning session, there were some discussions, and in Eric Horowitz's slides, there were some definitions of AI. To me, one definition of AI is the ability to learn from experiences. This is one definition if we agree to that. See, then this brings out that, so you look at the talk which we just heard, this amazing, exciting results in ranking and recommendation, etc., right? But the fundamental problem is, the premise is that I have some labels. So if you have to learn from experiences, who gives you the labels? We often don't have labels. And that brings us to this thought that maybe unsupervised learning is the way to go. If you crack that, then you master AI. And now here is some good news and bad news. If you believe in Elon Musk's catastrophic theory of everything is going to be under AI and we'll all be servants of whatnot, what we find is unsupervised learning is very hard. It will take another 30, 40 years before you can master this. So here's computer science way of resolving this issue, that unsupervised learning today seems to be intractable. And in the following slides, I'm going to express some of these views and say what is untractable about it and why is it untractable and that. But having said that, there is phenomenal progress is happening. So we can only say this, that it is intractable at the moment. In future, we're not sure. So having said that, so let us have this the usual spiel of supervised learning. So basically, we can take the first talk, the talk which we heard just before, as an example, and then go forward with that. So we are often given example. Let's say the diamonds and the pluses, right? And so if we have such labels and say that next time you show me an example, tell me it was a diamond or a plus. All of you who have done a basic course in ML will know, okay, so we can find some, some separation between them, maybe two lines you can draw like this, and one side of this line, there are the pluses, and other side is the diamonds, right? And so this has been the basis of this very famous SVM algorithm, etc. Now think for a moment and say, suppose I don't give you the labels, but just give you the data. Now what can I learn? Now here is the question. You will see the question is ill-posed at so many levels. I just give you this data and say do whatever you want. Now this is, I think, a fundamental problem where unsupervised learning is grappling with. So one very like we would not say a mathematical principle, but a philosophy behind this is, see, maybe you should find structure in data. Now that's a very ill-posed question. So we'll see how far this goes in the rest of these things. So this equation to me is one of the fundamental reasons of success of supervised learning. So here, let us assume for a moment we are in the labeled world. So where y are the labels and x's are your data points, right? So now you have to build a function where it takes in x and outputs to you a y. Now you want to say that if x and y have the same distribution, one can say that, see, this, what is the probability that you don't agree, that the prediction given out by f, it doesn't match y, right? So this is sometimes called the generalization ability, the ability to generalize, the ability to see unseen examples. Now, so this is sort of given by, so all you're given is some test examples, right? So the test examples, what you do is you measure your test set error. This I can do, right? Now there is this bound. So this bound says that your generalization error is your test set error plus a function g of h, where h is often, so if you're linear classifiers, h is often called the VC dimension. Forget it for the moment. What it says is that h is a measure of complexity of the function class. So the essential idea is this then, that you try to fit, if h is low, so suppose this was 0, then this would be equal. And g is an increasing function of h, right? So often, so the message of the story is get this low, training set error low, with h being low. So try to fit the simplest possible function or classifier, which gives the best training set error. You see? So that is the guiding principle. Once I have that, then I say, how will I control h? How will I control this training set error, this, that, where to go? Now think for a second, I don't have y. Now where is this? What is this side? I don't have any this, right? So this is this problem now. So even there's no formalism to think about, right? Now having said that, we'll see some examples now. Unsupervised learning is also making great waves, and I think that is the next wave in machine learning. So existing models are often intractable, yet works very well in practice, right? So now the need of the hour is, however, as we will see, that so there are some recent attempts which will try to make this problem tractable, but the problem is they don't scale. They don't work for large data. And as we said, our main premise is that in the world there are lots of data, but they're not labeled. So any unsupervised learning to be successful should be able to work on large scale data, any formalism I put. Now here are some things which are heuristic, works very well, but you're not sure, is it giving right result? And often people who have worked on unsupervised learning will tell you parameter tuning is a huge challenge. Of course, it's also there in deep learning. So the need for algorithms which are not only scalable, but they should also give statistical and algorithmic guarantees. This is the need of the hour, and I don't think we are there yet. So we'll see some examples as we go along. So here I've chosen unsupervised learning has, as I said, there is no fixed structure or a paradigm to think about. So many people think in many different ways. So one of the ways is that, maybe I've given lots of features. Can you bring it down to a very few features which are often called dimension reduction? So one of the dimension reduction is that, if data is there, you should go ahead and look at the direction of maximum variance. This often is known as PCA. This is a little bit well understood. Now think for it. So there is a variation of the problem where I said, okay, if I do PCA, what I am finding is that it's giving me a direction, but which is a mixture of all of the features. The price I pay is I lose interpretability. Interpretability means it must be able to tell you in terms of features. So this gene was active, that gene was active, and these 3 genes cause this. So that's interpretability. But if I say this in this subspace it lies, that doesn't often is not very interpretable. So a variation of that is sometimes called the sparse PCA. Now that becomes an NP-hard problem. Now there is this another very famous problem, and I think it's one of the success stories of unsupervised learning. You have gone to a cocktail party, right? I don't know why it has to be cocktail party, but here I guess you don't listen well, I guess, because of the drinks or alcohol or whatever. So imagine there are 3 speakers, and they're all talking against each other, and there are 3 microphones, right? In the party, you can all have meaningful conversations, but you're all talking against one another. Right? In the party hall, you can definitely make out who's speaking what. But let's do one thing. But let us now make the recordings available. And so the recordings can automatically find out who said what. Apparently, it becomes a huge messy problem. And that's one of the biological problem also. So it's a very famous cocktail party problem. Now that has been solved by what is known as independent component analysis. Now here, it seems PCA looks for correlation, or independent component analysis looks for independent directions. So where the search is for non-Gaussianity, etc., we will not get into that. But the main problem is this is again another intractable problem to find independent component analysis. So a simple versions of this problem you see is getting hard. So a major success story in unsupervised learning is probabilistic models. And probabilistic models, often there is this problem of inference where you have to figure out that what are the parameters and other things. These are again often become intractable. We said this intractability many times. But let's start with a very simple version of the problem, which all of us who have done ML, who have gone through ML course, you learn it in the first few lectures. Is can you find groups in data? How hard is that problem? So for example, the picture which we draw in the first few slides. Now you can take these slides and say, look, there may be 2 groups like this, right? But you see, I could have drawn another group here, right? And this 3 could be another group. So how many groups? If so, who goes where, right? These kind of problems is also not very well understood to begin with. So now what we will do is, taking this problem, we will look at 3 specific instances. One is clustering, which we saw. On clustering, one of the very famous algorithms is k-means algorithm. It's a very well-known algorithm. How good is it? Does it do anything interesting for that matter? We'll talk about non-negative matrix factorization. We'll talk about topic models very quickly. So clustering has many uses. I will not bore you with that, but probably one of the interesting uses where people looked at gene expression data and said, so you can these forms, so the red to green are different kind of clusters as given here, is to motivate the examples of clustering. So from understanding cancer biology, which was the previous slide, to here hard business, that can I segment the markets. So clustering has many uses. So now let's come back to our problem, what you said. So clustering is trying to figure out structure in data. What kind of structures? So find groups, okay? So what's the group? Group is nothing but a partition. That is, your data was there. Now can you partition them into some k number of sets, right? And which example goes to just one of the sets. And the question is, can you find those partitions? So one way to partition them is that maybe each set in the partition has a particular cluster center, maybe the most representative guy, and you take a data point and say which is the most representative of them, and you measure in terms of this distance, and you get what you get. All right. So this is a very famous clustering setup. Now there is a very nice algorithm. The algorithm is that you, in the first go, when you have these representatives, you assign them using this, that you assign them to the nearest cluster center, and then you update the cluster centers, right, using this simple formula. This is sometimes known as the k-means algorithm, 1957. We all know. It works very well also. The question is, when you say it works very well, it said, what do you mean works very well? I took data, I ran it, it worked. Right? Now, what can you guarantee with this? The problem is, if now what you do is, when you say it works well, often if you just change the data a little bit, you will see it doesn't work well anymore. So now, this does not seem to be that simple question to answer, that when will it work and when it doesn't work. So often, so this has led to very phenomenal, interesting work. So people thought about this, right? If you assume that each cluster, each example is coming from a Gaussian distribution with a certain mean and the variance, let's say, but if the means are well separated, so mu1 minus mu2 are the means, mu1 minus mu1 is the means, and they're well separated, right? That's the lower bound in terms of the variances. Then we have something. Then it can do. But then it says, if you believe in this argument, then you're saying, what are you saying? You're saying, the distribution must be Gaussian. Otherwise, it doesn't work. And that's what it's saying. That's what our understanding is. So then, a very interesting set of conditions came up by Kumar and Kannan. So here, where they're saying is that, see, you don't have to do this probabilistic thing, but what you can do is you can assume that if each data point, lies to the closest mean along a line joining so let's say you take a data point x and you take two other means cluster centers, mu L and mu S. If x is close to mu L, then it would be closer along the line joining this. Now, whatever it is, you see, this particular assumption is not probabilistic. It did not say in distributions, for that matter, right? So this was a very good progress, and they could derive, and they could show. Here's the more interesting part. They could show even then k-means didn't work. What they said was that if you want to really recover the clusters, that is the TLs, you do SVD first, then you run k-means. So even today, algorithm like k-means, we can only see that it works well when things are very, very well separated. And as things are closer and closer, I need to do something else, like you do SVD and do stuff like that, right? And people who are looking for smart, exciting problems, smart guys doing exciting problems, ask the question. Suppose I do not know k. That's we don't know. So we'll make some comments at the end of this lecture about this. So next thing, as I said, we'll look at matrix factorization. Now, so again, so one of the matrix which Malik alluded to, for example, the rating matrix, right? So D can be the number of items to be rated, and N can be number of customers. So now, if you can ask the web company guy, he will say D is like a million products, is quite common. How many customers? A billion customers. This is reality. I mean, this is why I'm not making this problem up. So now, how do I factorize these things, right? So A equal to BC is factorization. Now, the interesting part is what people have found is that most of the entries of A, let's say all entries of A are positive, non-negative. They can be 0 or non-negative. Now, if we say B and C also has to have the same non-negativity, then this problem is interesting from a practical standpoint, but also very hard. Now, but why non-negativity? Now, that part is not very clear, but Lee and Seung in 1999 in a very interesting Nature paper showed that maybe it compares the philosophy that maybe these B matrix then will help us decompose into subparts. So we'll see an example, but so this has found applications in text mining, hyperspectral imaging, and all kinds of other things. So the interesting thing is, this problem is again intractable. However, there are fantastic algorithms which works pretty well, but cannot guarantee you explicitly that did I find the right B and the right C. So just to be clear, what the example which I said, right? So now, if we run NMF or non-negative matrix factorization on a bunch of images, so I do not know if you can see this is like the eyes, there is something like the lips, there's something about the eyelashes and all that, right? So it's indeed finding some decomposition, which is like meaningful, right? So that is the reason why NMF has become so popular. And so this is our B matrix, and this is our C matrix, which is the multipliers. And you see this, if an original face can be represented by the C matrix, where B is my basis, and it can recover for me the of image which is pretty close to my original image. So NMF, that's why is called. So AI is also contributing to English language. There's a new word is coined now. It's called featureizer. So I have data, and now B is your features, and C are the coefficients, right? So this is the featureizer. So you see, this is very interesting here. Now the question is, but when does it give the correct decomposition? Now there's some first good news is NP hard. I said the simple problems, right? However, so they say, so see, it's not very useful to say is NP hard. I mean, so what? Because now can you make some assumptions on which is realistic? Yet, can you say, okay, in this case it's not NP hard if you assume some more things. So people said there's a nice idea about separability. Let's say that if B, so B matrix, right? This is like identity matrix here in our words, all right? And rest can be anything. So that is, there exists at least one word, if these are the words and N are the documents, let us say, or B, or let's say D is the number of items, as we said, right? If there's one item, which does not occur, which does not have any, let us say, the entry of the B matrix is 0 for in the other features, right? Or rather, let's call them factors for that matter. Let each column be a factor, and say that one item only, there are some special R items which appear, each of them appear only one of the factors, right? So then you have something like B equal to IR by B0. Now, under that condition, this is called separability, it is possible to find the correct decomposition. Now even algorithms for this was also not known. This was in 2003, right? Only after almost 10 years, this nice work came up where this algorithms based on simplicial factorization was proposed. And at that point, we can say, here is a provable scheme of finding an NMF, right? Now that was pretty slow. That was worked upon, and a new interesting algorithm was proposed called hot topics. But even then, it needs to solve an LP in ON square variables. What do you mean by that? Long story short, it will not work for your billion cross million things. It's too slow. That's the message you wanted to say, right? It's not with LP. So now here, so what we have been thinking about this problem, and said, so let's talk about another thing we observed, that existing algorithms, like what we just said, right, though they're provable and all that, but another problem with this, they're not at all robust. That is, you just add a little bit of noise, and the whole thing goes through. So now the idea is that can you develop algorithms which should have, they should be robust, they should be scalable, they should be provable. Now here, I mean, we'll not bore you to death, but we have an SVD based NMF algorithm which can tolerate a little bit of heavier noise. So this is a noise they can tolerate. That is, each column of N in its noise matrix, right, is like epsilon, right, in L1 norm, some norm. Whereas we can tolerate, on an average it should be epsilon. That is, some of the N's can have larger noise than epsilon. That's the point. That's we call heavy noise, right? So this is one of the things which we're doing. Now let's quickly jump, change track. Okay, so I think my time is up. So hence in the next 2-3 minutes, what I want to do is quickly tell you about a more interesting, a different area, which is often known as latent variable models. So here, latent variable models often say that there are observations and there are hidden variables, right, and often written like this. Now this is a very popular model. Your k-means algorithm can also be incorporated in this. HMMs can be incorporated in this. Your belief networks can be incorporated in this. Now to run such algorithms, you need to do EM, expression maximization. This one broad paradigm. However, now you say that if I show you enough examples, now can you recover the parameters? And that's NP-hard. Of course, there are Bayesian ideas and MCMC methods for that. They work well, but they lack these guarantees. So what we have done is we can you can use this one particular instance, and I will take just 2 minutes and do that. So one particular example of such a latent variable model is what we call as topic models. So now think like this, that we need to understand what a document is all about. Now if I say a document contains the following 5 words: run, inning, hit, season, game. What is the document about? Cricket, right? So if I say document contains about computer, software, system, Microsoft company, then that was not to publish as Microsoft name. It came out of a data set. So of course we're talking about computers, right? So patient, drug, doctor, cancer, medical. So you see, you didn't ask, I say the question was to what document is all about. You didn't ask for the verb, you didn't ask for the noun, you didn't ask for who wrote it. Just as 5 words told you something. So the question is that these are often called topics, right? So now these are you can relate to sport, and that's computers, etc. Right? Now the interesting part is finding. So I'll just quickly get So it is very difficult to discover these topics. Even these are NP-hard. So what we have made is, of course, building on the work of others, especially the separability assumption, we have been able to come up with an SVD-based algorithm. Just because I'm out of time to say this, right? Where is this? So I just go to the last slide just to show this, right? Now one of the questions was that, so many of you have used this algorithm called LDA, latent digital allocation. Now LDA doesn't guarantee you, or you can ask, how many samples do I need to learn LDA? This has been asked by industry people. Right? Okay, you run this, but how many samples do I need? Okay. Another point is, I run my LDA, but I set my K to be 100, and I all think I'm garbage. But I killed 50 worked well. So how do I resolve these problems, right? Now we have come up with an algorithm which just requires SVD, which means it can scale well, and it can recover this. If M's are the topics, it can come. M hats are pretty close to that, right? Now currently we are in work with Microsoft. We're trying to scale to like 1 billion tokens. And why is it possible? The point is that SVD is a very interesting algorithm which has been worked upon and it can be easily scalable. Now I just so we just made a comment about finding finding that K thing, right? Here also, in both the problems we present, NMF and our topic models, I still need to know the number of topics. Now if you want to ask, what if I do not know the number of topics? That's the reality case, right? Now that is sometimes called the non-negative rank. Now if non-negative rank was equal to rank, then things would have been easy. But you test that, when is non-negative rank equal to rank? That's also NP-hard. You see, life is so important. Also, non-negative rank has connections to a very, very deep notion in communication complexity. It's called non-deterministic communication complexity, an important quantity in combinatorial optimization. So the point being, I don't see this kind of problems get resolved very soon. So long story short, in summary, existing formulations of unsupervised learning algorithm lack guarantees, but we need them if we want AI systems to be more useful in practice. We will demand these questions. But if you to answer that, we are hitting against very hard problems in theoretical computer science. So I think most probably Elon Musk is wrong. And in the next 40 years, AI will not going to take over. I'll stop here.
On that very hopeful note, thank you, Chiranjeev. And we'll take probably 1 or 2 quick questions. Yeah, Mike, question here first, and then after that we'll go here.
Hi, sir.
Yeah.
Very nice talk. Thank you.
Thank you.
One quick question. So the idea of being robust to the noise, I think apparently that the problem is there across the machine learning. Even deep models do suffer on the problem. Right. So is there any general approach that we can take, from an optimization perspective or from a training perspective, how we can address this problem?
Okay, so there are two two things. So at this point, clearly we have to separate out supervised versus unsupervised. Okay. Now for supervised, for example, there is an area of work which touches upon robust optimization. For example, if you can look up some of my old papers also has done this. For example, data is missing values. So what can I do? So there are techniques for that. However, the same techniques will not apply for the problems in unsupervised learning, or maybe you do not know enough to unify these formalisms. So now we don't have to, if you ask a general questions, probably answer is we'll have to say no, I do not know of any way. But if you say for NMF, I see noise in A, what can you do? Okay, there may be some hope like that. But the same procedure may not apply to, let us say, topic models, or I change this, right? Or else we do not know enough at that generality. Right? Okay.
Yeah, we'll take one more question here. Yeah.
Thanks, that was an interesting talk.
Thank
so
you.
You talked about the non-negative rank being NP hard.
Right.
I was wondering if there is any way, like in practice, we need to do non-negative factorizations, and then what's the general guideline to tune this rank parameter? Because we work with tensors, in which case the rank itself is NP hard.
Exactly, that's what I'm saying. So now at this point there are no guidelines for say, except to say try out everything. So one option is that, okay, for sure we can do the following thing. Non-negative rank is NP hard, but you can compute rank, and rank for sure is a lower bound on non-negative rank. So whatever R I should choose, it should be more than the rank. This is the first thing, right? So, and what I am trying to say is that beyond what I have written, there is no further insight at this point. Now, there is another very exciting line of work which I didn't get time to cover. It's called Bayesian non-parametrics, right? So there, using suitable priors, one can maybe hope to get a better estimate. Again, but it does not give you a guarantee that, does it have this? It is again, guarantees are very, very loose.
Most often the non-parametric models are very hard to, like they take a lot of time
and to tune the parameters.
Yeah,
the reason is, and the reason is that, the guarantees are so weak. We would like, if you ask, we want to ask a question like this: how many samples will I need? Would I recover? What is my error? So unfortunately, the mechanism is cannot deliver you these results because their main thing is guided by in expectation. This is what you get, which is often not very useful.